Hi guys, and here we are. We're going to review chapter 5 here for 8th grade math. But first I want to bring your attention to a game of Battleship. I hope you guys have all had that chance to play, and your opponent hides these ships over on the other side, and then you try to guess the coordinates so that you can sink that ship. But I want you to imagine a little bit different game where instead of all these ships everywhere, you're just trying to find that one point. So if you had two ships that were actually traveling, and one was represented by this red path and one was represented by this white path, you're looking for that point where they crash into each other, right? Or where they intersect. And you could guess and check all these different spots. But what if I told you, if you knew the equation for this line to tell you which path this red ship is taking, and you knew the equation for this white line, you actually have three different ways that you could pinpoint that exact location without guessing all 100 different spots here. In the long run, this will save you a ton of time and have some real life applications. So hold on to your horses. We're going to do uh, our first strategy, which is solving systems of linear equations by graphing. Now, when you're solving systems of linear equations by graphing, you have to be super duper precise. And there are really three steps. You're going to remember these steps from our study guide that we printed out at the beginning of chapter 5. And you also see these steps right here. So you notice step 1, graph each equation. Now, this is not going to be a sloppy, haphazard graph that kind of looks like that because you're not going to end up with the precise coordinates of the location where those two lines cross if you are not precise with your graphing. So step 1 is graph each equation. You have an equation y equals negative 2x. Your first question is, what form is this equation in? You may have some memory of seeing it as slope-intercept form. We know our y-intercept would be here at 0, right? So it's going to cross through the origin there. And then our slope is negative 2. So we're going to go down 2 over 1. Down 2 over 1, or you could go up 2 to the left 1. And that would be your first line. Now our second equation is y equals 3x plus 2. So ask yourself, what form is this in? It's in slope-intercept form again. Our y equals mx plus b. Now this number in front of x tells us the slope. The number out here tells us your y-intercept, right? So our y-intercept is going to be up here at 5. And the slope is going to be 3. So you could go up 3 over 1, up, but it looks like it's actually going to cross down here. So if we go down 3 to the left 1, we're still going to have that line with positive slope. We're going to get out our ruler because precision does matter. But if you go from this y-intercept and count down 3 and over 1, you can see with certainty that it's going to cross right there at that point. Now, when you're solving a system of linear equations, your solution is going to be in the form of an ordered pair. So first we're going to have the x value, which here is negative 1. And then you're going to have the y value, which is 2. And that is your solution for the system of equations that we have here. Now, if you look over here, step 3 is check the point from step 2. This is a critical step because if you're ever solving a multiple choice test, you want to be able to prove that that point actually fits into this equation and is true. So you're going to take your y coordinate, your 2, put it in where you see a y. You would put your x coordinate in wherever you see an x, just like that. Okay, and then you'd say, does 2 equal negative 2 times negative 1? Well, negative times a negative is a positive, so you'd end up with 2 equals 2. And yes, that does check out. Now down here for this equation, you're going to put in a negative 1 wherever you see an x, and you're going to put in a 2 wherever you see a y. And then you're going to test, is 2 equal to negative 3 plus 5? Yes, it is. So I'm going to work through the even problems here, and you guys are going to notice number 2 looks like this that I have written on the board. Now we're going to solve this by graphing, and the first question you're going to ask is, what form is the equation in? So I'm going to just make this bigger so you guys can all see this. So as we look at this, we see this top equation is in slope-intercept form, y equals mx plus b. Okay, this bottom equation is in standard form. So you could graph it in standard form using what you know about intercepts, or you could rewrite the equation so that it is in slope-intercept form. Okay, So in order to rewrite the equation, we want to get y by itself. So we're going to subtract anything else that is on the same side as y. Then we end up with 3y equals negative x. Divide both sides by the coefficient in front of your y term, and you end up with y equals, we're going to rewrite this as negative 1/3 x. And that's just so that it looks more like our y equals mx plus b format, because x times a negative 1 is still negative x. We haven't changed anything, we've just kind of reshaped how that looks. So now we have an equation in slope-intercept form, and this one was already in slope-intercept form, and we can graph them. Okay, so now we're going to graph this. Our y-intercept is at 4, and our slope is a negative 1. If you don't see a number out in front of the x, you're going to assume it's 1. If it's a negative out there, you're going to assume it's a negative 1. So we're going to go down 1 over 1 and build out our line kind of like that. Now for this one, we don't have anything added to the end of our x, so we know it's going to pass through our origin, 0, 0. Now a slope of negative 1/3, we're going to go down 1 over 3. Down 1 over 3. And if we build it out that way, just using dots to expand our slope, we can find with precision that it is going to cross at this point, which would be what? 6, negative 2? Okay, so we've done step 1. We have graphed our equations. We did step 2. We estimated the point of intersection. Step 3 is to test your solution. So you're going to put, remember, this is an xy form, right? So you're going to put 6 back into this equation and test to see if it works out. So you would end up with y is negative 2 equals negative 6 plus 4. Does that check out? Does negative 2 equal negative 2? Yes, it does. So we are A-OK. Then we're going to put these values back into this equation. So we would say y is negative 2 equals negative 1/3 times 6 over 1. Now we would say negative 2 equals, if you don't cross cancel anything, you would just have a negative 6 over 3, which would work out to negative 2 equals negative 2, and you'd say, hooray, our solution is correct. So we did find the exact coordinates where these two lines cross. Our next strategy is solving a system of linear equations by substitution. Step 1. Equation 1 is already solved for x. So step 1 is actually solve one of the equations in terms of x equals or y equals. That's what you want to look for, okay? And then whatever this whole of y equals is equal to, you're going to put that into your second equation anywhere you see a y. So let's take a look at what that looks like in this situation. So we have x equals 1 plus y, and I'm going to circle it and draw an arrow. So down here in this second equation, you are going to substitute in 1 plus y in place of where the x was. Then you're going to add 3y equals 13. So the only thing that changed is that instead of this x, we substituted in this value that we got from the top equation, okay? So now if we look down here at this equation, we notice that the only variable we have is a y, which is awesome because just like the game of Clue, if you only have one variable in an equation, you can solve for it. So we're going to combine like terms. Y plus 3y is 4y. We still have the 1, and that's all equal to 13. Now we want to get y by itself, so we're going to say, what's the opposite of adding 1? Aha, subtracting 1. Then we have 4y equals 12. And to get y alone, we're going to divide by the coefficient out in front of y. When we do that, we have y equals 3. Are we done? No, because you're going to take that value for y, put it back up into your original equation, and solve for x. So when you do that, you'd have x equals 1 plus this value for y, which is 3. So you'd say x equals 4. And then you have everything you need to write your ordered pair that would tell you where these two lines are going to cross. So we didn't have to graph it. We just used substitution to solve for that ordered pair or the solution to the equation. So let's do a couple of these. Let's do Let's do number 6. It's a little bit more complicated. So number 6 says negative x plus 5y equals 28, and x plus 3y equals 20. Okay? Now the first step is to solve one of the equations in terms of x equals or y equals. And I like this one because there's a standalone x. And so we could easily just subtract 3y from both sides and rewrite our equation as x equals negative 3y plus 20. Okay? Then we're going to take this entire value here and we have to substitute it into the other equation. We can't substitute it back into the equation that we just changed. So we're going to take this equation and we're going to say negative x, which is negative 3y plus 20, plus 5y equals 28. And all we did was take this equation, and anywhere where we had an x, we put this whole value in for the x. Do you see that? But we have a negative out here, so we have to use the distributive property to get rid of the parentheses. So this would, negative times a negative, it was going to be just 3y. Negative times 20 is going to be minus 20 plus 5y equals 28. Now we're going to combine like terms. So we look for our y's, combine those. We end up with 8y minus 20 equals 28. To get y alone, we want to do the opposite of subtracting 20. So we're going to add 20 to both sides. Then we have 8y equals 48. Now to get y alone, we divide by the coefficient in front of y on both sides. That cancels out, and we have y equals 6, which is great. Then we put that back into either one of these equations and solve. So if we say x plus 3 times y, which is 6, equals 20, we are going to be able to solve for x. So x plus 18 equals 20. Subtract 18 from both sides, and x equals 2. So we can now write our ordered pair for the solution to this system of equations. So my encouragement to you is this. If you do not see one of the equations solved in terms of like y equals or x equals, you have to change the equation around until you get that part. That is step number 1. Step number 2 is substitute it in to the other equation. Okay? Step number 3 is solve for the value of that variable. Step number 4 is substitute that value back into one of your original equations and solve for the value of the other variable. And we don't have this technically, but write the ordered pair. The final method is solving a system of linear equations by elimination. I have to tell you, this is my favorite. You get to stack them up and make one of the variables vanish, which sounds pretty good. And then you get to solve for the other value of the variable. So let's give that a shot. Sometimes writing the equation is the trickiest part. So number 7 is on your homework. We're going to talk through this. So you have a gift basket, you have jars of jam, and packages of bread mix. This sounds like Aladdin. Okay, so let's say we have jam, that's X, and we have packages of bread mix. Let's have that be Y, and the total cost is $45. Okay, now there are 8 items in the basket. Jars of jam cost $6 each, and jars of bread mix cost $5 each. So if we were finding the total value, this would be our equation. But we can write another equation because we know that x plus y equals a total of 8 items. So that is the trickiest part, is writing the equation from the story problem. Okay. Once you have written that, then your first step is to scroll up here, multiply each equation by a number so that you have opposites. So if we multiply this whole thing by -5, then we would have opposite equations because the opposite of 5y would be a -5y. So let's do this. So we would have -5x minus 5y, because negative 5 times y is negative 5y, equals negative 5 times 8 would be negative 40. Okay, so let's go ahead and rewrite this equation down below. Our top one, 6x plus 5y equals 45. Now, when we're eliminating, we're going to add them together. So negative 5x plus 6 is just going to give you x. And when your variables are stacked up, you just get to add them straight up. These are stacked straight up. That's going to add up to just 0. So it's eliminated. That term is eliminated. And negative 40 plus 5 is just going to be 5. So x equals 5. Hooray! Then you put that value for 5 back up into one of your original equations. So we could say, let's see, x is 5. If we put it back into this one, 5 plus y equals 8. So we would subtract 5 from both sides and know that y equals 3. So our solution would be 5, 3. Now we're going to test this, right? So if we put it back into this equation, does 5 plus 3 equal 8? Yes. And for this one, I'm going to actually write this out. 6 times 5 plus 5 times 3. Does that equal 45? So this would be 30 plus 15. Does that equal 45? Yes, it does. So we did find the solution. Now you need to be able to interpret what this solution means. So if you remember, our x term was talking about the number of jars of jam, and our y term was talking about the number of jars of bread mix, or a number of boxes of bread mix, okay? So at this point, when you have 5 jars of jam and 3 boxes of bread mix, you have a total cost of 45 and a total number of 8 items, and you've satisfied both equations. Now, every system of equations is special, but there are some that are especially awesome. And there are a couple things that I want you to look out for. Sometimes you're going to end up with a system of equations that is actually parallel lines. And so that's the situation we're in with A. You're going to notice they're both in slope-intercept form. And the slope for both of these lines would be a negative 5. Now, this is a positive slope, but if you were to imagine, if they have the same slope, they're going to be parallel lines, meaning they're never going to cross, and there is no solution. Because that's the definition of parallel lines. They go on for eternity and never cross, so you're never going to find a solution there if they have the same slopes. Now, let's look at a different system, or a different special system of equations. Here in this example, you're going to notice just the basic structure of a system of equations is if they have different slopes and different y-intercepts, they are going to cross at some point. But I want you to take note of this, the form of this original equation. We have x plus 1 equals 1/3 x plus 3. So these two things are equal to each other. So if we were to say A equals B and B equals C, we could say A equals C, right? And so that's essentially what we have done, is we're going to say this part is equal to, instead of B, we're going to say Y. And then we're going to say this part, which is our C, is equal to Y. So we're going to say this part equal to Y and write one equation, Y equals X plus 1. And then we're going to take this part and set it equal to Y. And we're going to have Y equals 1/3 X plus 3. Now, I don't know that you guys solved any problems like this before, but I want you to know that you can do that because you're setting, these were equal to each other, and now you've just set them equal to the same thing, y. And now we have both of these that are in slope-intercept form. You can graph them and find the point where they intersect, and then test that point and make sure that you do have the solution for that system of linear equations. And two lines that cross are going to have one point or one solution. Now, the final bit I want you to see is when there would be a system of linear equations that has infinitely many solutions because it's actually coding for the same line. So if on number 9, here's your first equation, and then here's your second equation, 9x minus 6y equals 3. You're going to notice a lot of similarities here. And I want you to notice that if you take this and you multiply the whole equation by 3, you would end up with 9x. We're going to use our distributive property minus 6y equals 3. So this equation and this equation are actually the same line. And when it's the same line and you have one line and then you draw another over top of it, they're overlapping. So you would say this has infinitely many solutions. Okay? So you're going to look for that kind of parallel structure in the equations. And if you can multiply the entire equation by one constant and get the next equation, you know it's actually going to be a system where there's infinitely many solutions. All right, that's it. So you are using those 3 different methods, graphing, substitution, and elimination, to solve systems of linear equations and analyze and interpret what those solutions mean. So you have infinitely many solutions if it's the same line, you have one solution if it's crossing at one point, and you have no solution if it's parallel lines. So good luck on this chapter review. Make sure you get all your work in by Wednesday. Thanks, guys.